We have two more translations to look at, or types of translations. One is vertical shrinking and stretching. The other one is horizontal shrinking and stretching. And then we're going to pull it all together and look at what happens if you have a bunch of things going on inside a function. What does it look like? I can't emphasize enough why this is valuable. My students in calculus who struggle are the ones who, when I put a function up on the board, don't know what that looks like. So it's valuable to you to recognize, hey, that's a parabola. Hey, that's an absolute value, so it's V-shaped. That cubic function, whatever it is, to know those parent functions, and then to recognize that when this particular thing adjusts that parent function, how does that impact the graph? That's kind of the reason for this section, is to be able to recognize functions more easily than if you had to plot points. That idea where we used to create a table of values to figure out what a function looks like. One, it's a little bit archaic or unsophisticated, whatever word you want to use, in that if you don't pick the right points, it doesn't necessarily give you a full picture. So for example, if you plotted points to try to plot an absolute value function, but you only plotted, let me scroll up here, if you only plotted positive x values, you may think it's a line because you're only going to get this part of that, right? So recognizing that an absolute value function is going to give you a v of some format is so valuable, or recognizing a parabola or whatever. So these are super valuable to know what they look like as you move forward and you progress in your mathematical career. Let's go back to vertical shrinking and stretching here so that we can start to recognize what do all of these things do. What happens with vertical shrinking or stretching ultimately is you're going to be multiplying the y value by a constant, by some constant. We have shrinking if that constant is between 0 and 1. And we say shrinking because it shrinks the values closer to the x-axis, because it makes all of the y values smaller while leaving the x values unchanged. Let me give you an example here. This g of x equals 1/2 x squared shrinks that standard parabola by multiplying each value of y by 1/2. You're multiplying the y values because it's outside of the square, right? There's a big difference between 1/2 x squared and 1/2 x squared. In the first case, the 1/2 is after the square. In the second case here, the 1/2 is before the squaring. So those are two different things, and so the impact on the graph will be different. Let's graph our standard parabola. An important thing about the standard parabola, it goes through the origin, because when x equals 0, y is 0. When x is 1, y is 1. When x is 2, y is 4. So we're up here. When x is 3, y is 9, because you're squaring, right? This is a squaring function. 1, 2, 3, 4, 5, 6, 7, 8, 9. So we're up here. Let's go with some negatives. When x equals -1, y is 1. We have that symmetry over the y-axis. So we get these points if you were to plug in values there. Okay, so that's our standard parabola. Oops, make sure we actually come down and hit that vertex down here at the origin. Now, when we talk about multiplying each y value by 1/2, what we are saying is that for the same x value, y is 1/2. So let's do it with a table of values, and then we can talk about, do we really need that? See? y equals x squared, and then we'll do y equals 1/2 x squared in the same table of values here. So we did in our graph over here, we did -3, -2, -1, 0, 1, 2, and 3 for the x values. On the y equals x squared, we get 9, 4, 1, 0, 1, 4, 9, because those are what happens when you square each of those x values. Now when we do 1/2 of that, we get 9/2, we get 2, we get 1/2, we get 0, and then repeat those, 1/2, 2, 9/2. Let's go ahead and graph these y values that we created in the right-hand column here with those numbers in the x, so those ordered pairs. -3, 9/2. Well, 9/2 is 4.5. That is going to be here. So notice that point that was up at -3, 9 is now at -3, 4.5, cutting that or shrinking that down to the x-axis, cutting it in half. This point was at -2, 4. Now it is at -2, 2. That's the y value. This point, erase that mess we have a little bit there. I'll regraph that. The point that was at -1, 1 is now at -1, 1/2. So it's cut in half. The 0 doesn't change. The vertex doesn't change there. And on this side, we get the same impact. These y values are all cut in half. So we get this parabola where all of my y values get cut in half, so it kind of like lays down. It's a wider parabola. So that's the impact of the 1/2 on the outside. That is a vertical shrink. A vertical stretch is if that number is bigger than 1, then we do the exact same thing, but now the numbers are getting bigger than they originally were. So this 2, now instead of our x's -3, -2, -1, 0, 1, 2, and 3, giving us y equals x squared, giving us 9, 4, 1, 0, 1, 4, 9. Now with the 2 in front, those numbers double. 18, 8, 2, 0, 2, 2, 8, 18. So I'm not going to graph the original parabola, but you're going to see that when I graph these, first of all, I still have the vertex at the origin. Now instead of 1, 1, I'm up at 1, 2. And instead of at 2, 4, I'm up at 2, 8. And then those reflect over. I can't even graph if I keep the same scale, I can't even graph the other one, the last one, the 3, when x is 3, because it's off my scale here, off my graph. Notice this parabola is much narrower than the blue one. It's narrower, it stretches it away from the y-axis, which pulls things away, which with the parabola makes it narrower. We talked about the scenario where c was between 0 and 1, so it's that fraction between 0 and 1, shrinking it, pulling it closer to all the values closer to the y-axis. We talked about the situation where c is greater than 1. If c is 1, it's uninteresting. It's the same as the original function, right? But we didn't talk about what if C is negative. C being negative means we have both a stretch or shrink, depending upon what that number is. Oopsie. And a reflection. And because it's on the outside, it's a reflection over the x-axis. That negative on the outside gives that reflection over the x-axis. So, for example, if you had g of x equals negative 1/2 x cubed, you're going to take, I'm going to do a super rough quick sketch here. Cubic function looks like this. Y equals x cubed. That function is going to both reflect and shrink it by 1/2. So it's going to get wider and reflect over. It gets wider from the 1/2, and this is not an exact picture, but just to give you an idea. And then the negative gives the reflection. Okay. Let's talk about our last translation, which is horizontal shrinking and stretching. Very, very similar. The behavior, though, is changing the x values. And just like with the shifts, those translations, horizontal translations, left or right, the opposite of what you would expect happened. The same thing happens here. Instead of multiplying by that number, you have to divide by that C value on the inside. You divide the x coordinates by that. Let me show you what I mean. This function, we have x. Normally, on our absolute value graph, we would do something like this. Let's just go with these 5 points. -2, -1, 0, 1, and 2 would give you 2, 1, 0, 1, and 2 on the standard absolute value. Now, if we want to look at g of x equals 2x, we have to do divide each x value by 2, which is the same thing as multiplying by 1/2. So we're going to say -1, -1/2, 0, 1/2, and 1. And now our ordered pairs for this g of x function, for this guy, are going to be these. Just be careful to keep them in the right order. These become our new x's. So when x is -1, the y is still 2. When x is -1/2, the y is 1. 0, 0. 1/2, 1. So notice I'm halfway in between there. You know what, let's do something different. Let's make the scale a little different so we can see this better. Let's call this, let's go 1, 2, -1, -2. 1, 2, -1, -2. And then when we go to let's graph the standard parabola first. It goes through here. We do the same scale up here. 1, 2, that's going to be y equals the absolute value of x. Now let's graph this other graph so you can see how they relate. Now we have when x equals -1, y is 2. So we're up here. That's that ordered pair -1, 2 from this. Then when x is -1/2, y is 1. 0, 0 still. When x is 1/2, y is 1. And when x is 1, y is 2. So we're up here. We also have symmetry still. So this is our g of x equals the absolute value of 2x. So notice that it kind of, when you do 1/2 of the x's, it kind of shrinks to the y-axis. Just like when you shrunk vertically, it shrunk to the x-axis. That's kind of what's happening here. You're getting closer to that x-axis in this, in the y-axis in this case. Here, a similar result. Let's do the square root function. This one, instead of actually graphing it by hand, you could plot some points. What I've decided to do for this, I'm actually going to graph this, show you this in Desmos, which is my preferred graphing tool. Even over your graphing calculator, I think it's so you can see things a little bit better. So I'm going to graph this square root of 1/2 x in here. I equals square root of 1/2 x. Okay, let me move this around a little bit. Our normal points, let me graph the traditional square root function. So that top one, that purplish one, is your normal square root function. It goes through 0, 0. We see a point at 1, 1 here. We'll see a point at 4, 2, right there. You'll see a point at 9, 3 there, and so on. So what happens with these when we use those same values, when we divide the x's by 1/2, dividing by 1/2 is the same as multiplying by 2. So for this same y value that we had here that was at 1, 1, now it's going to be at 2. On the green one, it'll be at 2, 1. The point that was on the original function at 4, 2, now that x value gets doubled to be 8. That's this point here. 8, 2. Same thing, you can keep going. In the square root, traditional square root function, the square root of 9 is 3. That's where you get this point, 9, 3. Then you double the x, and it's going to take you all the way out here to 18, 3 on that green one. And you're doubling it because we're dividing by, there it is. Dividing by 1/2 is the same as multiplying by 2. So that's what happens with that graph. You can kind of play around with these a little bit in your graphing calculator or in the calculator in your, if you're using Alex in there. Okay. Again, what if the C is negative? We have that reflection. So you have the stretch. What is going on here? What is going on with my brain? Stretch, or I was combining stretch and shrink at the same time. Stretch or shrink plus a reflection, and if it's in this case on the x, if the C is impacting the x, it's a reflection over the y-axis instead of the x-axis. Okay, so order of operations is super important. I kind of put a picture here to talk about what are we doing, how can this all be combined. This picture shows all of the things, okay? if you plugged in a value for x, the first thing you would have to do is subtract the h from it. That h is that horizontal shift is going to be first. I don't memorize this, I just think about what would I have to do. Then I've got this negative b multiplied by it, right? The b is that stretch or shrink. Compression is what this image is calling it. And the negative is that reflection about the x-axis. So we're going to do the horizontal stretch or shrink and horizontal reflection. Okay, so that'll be second. Then third, if we come back down here, our next thing is that we apply whatever happens inside there. The function operates on it, right? So that is your absolute value. That's your square. That's your cube root, whatever it is. Then order of operations, this guy is going to come next because we multiply before we add or subtract. So we are going to do our vertical stretch or shrink and vertical reflection would be next. And then last, you're going to add or subtract there. So that is your vertical shift translation. That's what that's technically called mathematically. Up or down. Okay? Let's look at least one example here. I think we have two examples to look at in this. Yeah, let's do these two examples and then we'll take a look. We'll wrap this up. Okay, so whatever the function is here, it is given in this picture. Whatever equations describe that, it doesn't really matter. What matters is that we have these three things happening. We've got this 1/2 multiplied times it. We've got this +1 added to the x inside there. And then we've got this +2 outside of the function. Again, thinking about order of operations, this x, if you plugged in a number for the x, the first thing you would have to do is add 1 to it. That is your horizontal shift if you're impacting the x, and that is a left shift by 1 space. Okay, remember that horizontal is the opposite of what you would expect. Next thing we would do, I'm going to call this step 1. This is 1. Next thing we would do would be this guy. So step 2 here is a shrink, vertical shrink by 1/2. And I don't want you to necessarily memorize all this stuff, but just think about how that 1/2 is multiplied by the function, and the function represents those y values, right? The output of the function is the y values. So that's why we are multiplying all of the y values by 1/2 in that step. Now let's do our third step. Step 3 will be a vertical shift, and specifically it's going up because we're adding 2. Let's try to graph this. I'm going to do it in the whole thing in, let's go red so we can really see it. Okay, we want to take all these points, we want to shift them left by 1, we want to shrink them by 1/2, and then we want to shift up by 2. I'm going to start with this point over here that is at -3, 4. If I shift it left 1, it goes over to the left 1 space. Shrinking it by 1/2 takes that y value of 4 and makes it 2. So I bring it straight down to be at -4, 2. Then I got to shift up by 2, takes it actually back up to this point. Let me go through that one more time. I just moved this point here, shifted it left by 1, that takes it over to -4, 4. Shrink by 1/2 is going to take it to -4, 2, because I'm multiplying the y value of 4 by 1/2. Then shifting up 2 will take it back up to -4, 4. Okay. Let's do this point that's at 1, -1. Let's do the exact same thing. And then we will connect to those 2 dots because the relationship between those is still going to be linear. Okay, we're at 1, -1. Shifting it left by 1 takes it over to be right on the y-axis at 0, -1. Shrink by 1/2 will take it to this point, because you're taking that y value of -1 and multiplying it by 1/2. So that takes us to -1/2 on the y value. Now I need to shift up 2 spaces. 1, 2 spaces. It's actually going to be here. Let me erase this one. This was sort of an intermediate step. And I'm going to connect those 2 lines, or those 2 dots with a line. That represents the line connecting -3, 4 and +1, -1. Let's work on these 2 points. The one at 2, 3, shifting it left by 1, goes over to 1, 3. Shrink by 1/2, y value of 3 multiplied by 1/2 is 1.5, or 3/2. So we're at 1.5. Now I have to go up 2 spaces. 1, 2, up to 3.5. This guy should be, because we're not changing the relationship horizontally there, should be 2 spaces to the right of this. It should be here, but let's double check. 2 spaces to the right of that one we just did. Let's double check. We were at 4, 3. We shift it left 1. Goes over here to 3, 3. Shrink by 1/2. We'll take it down to, remember the y value is 3, so half of that is 1.5. Now go up 2 spaces to 3.5. So yep, that's where we are. Just an intermediate step there. Okay, so let's connect those 2. And these 2 lines. That red graph is the graph of 1/2 f of x plus 1 plus 2, given the blue one being f of x. One more example. I know this video is getting long, so hang with me here. This is an actual function with a parent function instead of just being given the original graph. Let's look here. I'm going to graph the original function. The parent function here, or that standard function, is y equals x cubed. Goes through 0, 0, goes through 1, 1, it goes through 2, 8. Yeah, we'll stick with that. And it goes through -1, -1, -2, -8. Down here. I'm just cubing those numbers, right? The x values to get the y values. Clean that up. It needs to be nice and clean so we can see what we're working on here. Okay, we get this sneaky looking thing here. Let's write down our transformations. Let's go yellow for the first one. That's this guy. We are going to shift right 4. Feel free to pause the video and try and write these down on your own and see how you do. Shift right 4. Then let's go to here. I am going to shrink by 1/2. Then I have this negative is going to reflect over the x-axis. And then one more, let's go this, is this guy. We're going to shift down 3. Whew, this is a big one. We got a lot going on here. Okay. I'm going to start with those key points that we had. Remember, in our original function, y equals x cubed, -2, -1, 0, 1, and 2. Those became -8, -1, 0, 1, and 8 when we cubed them for our y values. Let's start with the origin point here. Let's shift it right 4 spaces. 1, 2, 3, 4. So we're here at 4, 0. Shrink by 1/2 doesn't change it because when you multiply that y value by 1/2, I should clarify that's a vertical shrink. So when you multiply that y value of 0 by 1/2, it doesn't move. Reflecting over the axis doesn't move. And then down by 3, 1, 2, 3. That is where this, what we call point of inflection, where it changes that curving, is going to be. So 0, 0 went to, what is that, 4, -3. Let's look at 1, 1 and where it goes. Right by 4, 1, 2, 3, 4, over to 5, 1. Shrink by 1/2, we'll take it to a y value of 1/2 instead of 1. So now we're at 5, 1/2, right in the middle here. Reflecting over the axis is going to flip it down here and then shift it down 3. 1, 2, 3. Down here. Let me get rid of those other 2 points that were kind of our help us think through it points. Okay. So the point 1, 1 moved to 1, 2, 3, 4, 5, -3.5. Okay, let's look at 2, 8. And then from there, we might be able to use some symmetry to help us because this axis has, or this function has origin symmetry normally. The function we're finding will not have origin symmetry, but it still has symmetry around that turning point there. Okay, 2, 8. We're going to move it over to the right 4 spaces. Takes us to 6, 8. Then we shrink by 1/2. Here was where we first, with our shift. And 1, 2, then shrink by 1/2. Takes that y value of 8 and makes it 4 here. Now we're at 6, 4. Reflected over the axis is going to take it down to -4 for the y value here. And shift down 3. 1, 2, 3. Down here at 7, -7. Erase these other sort of intermediate points. I don't want us to think those are part of our graph. They just helped us see where we were. So now that went to 6, -7, I believe it is. 2, 3, should have been because we were at -4 and then shift down 3. Okay. So we have this as this part of this graph after the transformations. We could do the same thing with -1, 1. Shift it right 4 spaces. -1, -1. 1, 2, 3, 4. Over at 3, -1. Shrink by 1/2 is going to make it here. Reflect over the axis puts it up at 1/2, y value of 1/2. Then shift it down 3 from there. 1, 2, 3 takes it here. And that point is what? 3, -2.5. And this last guy, -2, -8. Move it right 4. 1, 2, 3, 4. Shrink by 1/2. That y value of -8 now, when you multiply that by 1/2, is at -4. So my x coordinate is 2, +2 from the right shift. The shrink by 1/2 is now -4. Reflect over the axis takes it up to +4 instead of -4. And shift down 3, end up here. So erase these points that were just sort of our intermediate points. So that point is 2, 1. Get this picture. So let's think about now. We shifted it right 4 and we shifted it down 3. So we definitely are seeing that. The reflection over the x-axis is what turns it from an increasing function to a decreasing function. The shrink by 1/2 is what's making the shape a little bit different. It's making it squatter, closer to what would have been the x-axis. So that is transformations. This is a lot. I hope that you paused this at some point in this video and took a little breather because it is a lot here. Be sure to ask if you have questions. This is not an easy topic, but it's an important one based on what I was saying earlier about being able to recognize generally what these functions are going to look like. Looking at this equation that you're given here and recognizing, oh, it's a cubic function, so I get that sort of snaky looking thing. And then I'm shifting, I've got some stretching, I've got a reflection to make it snake the other way. So those are important things to recognize so you know what this function, at least generally, is going to look like.